Do you like books? I mean, really, really like books? Then you're in the right place. Each week, your host, Sam Hankin, interviews the best of today's top-selling authors and the up-and-coming superstars of modern literature. This is The Avid Reader. Here is your host, Sam Hankin.
Good afternoon, everyone, and welcome to another edition of The Avid Reader. Today, our guest is Dr. Lisa Feldman Barrett, author of 7.5 Lessons About the Brain, published on November 17th by Houghton Mifflin. Lisa's previous books include How Emotions Are Made, Handbook of Emotion, The Psychological Construction of Emotion, and The Mind in Context, among others. I suggest that you take a look at her TED Talk and also check out her episode of Through the Wormhole with Morgan Freeman, which I really enjoyed. The great thing about this book is that it's accessible. As Lisa says in her introduction, the short, informal essays are designed to intrigue and entertain. And then if you want to delve deeper, you can check out the full scientific references at 7.5lessons.com. And then the appendix will take you further down, if you will, the wormhole that is the very tool you use as you read this book. So I've always thought that it's interesting that when we're studying the brain, we're using the very tool that we are examining as the tool we use to examine it. We have 3 pounds of wetware, and Lisa opines that that is what makes us human. In an ethical and moral sense, the book's lesson is to think, that is, to think about who you are and who you want to be. So welcome, Dr. Barrett, and thanks so much for joining us today.
Oh, it's my pleasure. Thanks so much for having me.
So let's talk about the lowly ambiosis. How do you hearken us back to our own beginnings in that fashion?
Yeah, so the little, it's a hard word. It's a lancelet is the modern term, but the technical term is amphioxus. Amphioxus. It's hard. It took me a while. I had to practice it in front of a mirror. And amphioxus is actually a modern creature, but it's a creature whose environment hasn't changed much in 500 million years, give or take. And so when we look at the genetics of this animal, we can see that it's very similar to what would be a common ancestor that vertebrates, that is animals like us with backbones, have with invertebrates. So it's a really ancient animal. And it has ancient roots. And the really neat thing about this little creature, it's kind of like it looks like a little worm until you notice that it has gill slits, which are what fish have, and it has no brain. It has no brain, it has no eyes, it has no ears, it has no head, actually. So it's not really aware of its surroundings very much, and it doesn't have a brain. And so it's the perfect place to start the adventure of trying to figure out why do we even have brains in the first place? Like, what's a brain good for? Why do we even have this, this 3-pound blob between our ears is super expensive. So why do we even have it? What's it good for?
It's funny because that creature reminded me of Eric Kandel's buddy, the Aplesa.
Right.
Basically this big slug that has 20,000 neurons versus our, as you said, 128 billion. And he used that to discuss memory, which you've also discussed. And it's so fascinating to me that we have these templates that we can use to extrapolate out to us. And you do a very good job of doing that.
Thanks.
So that if we go seriatim, and I don't know if we'll go through all of them, hopefully we will. So the half lesson gives us the idea of, I'll just pick one theme that I liked, the idea of budgeting. And what's interesting is you actually compare it to a financial budget, almost like an Excel spreadsheet.
Right.
Assets and debits. How does that work? Does that metaphor work?
So the technical term for body budgeting is allostasis. And that means that your brain is predicting the needs of your body and attempting to meet those needs before they arise. And so your brain, in order to regulate your body or keep your body healthy, is budgeting. It's not budgeting. You can think of it as running a budget. It's not budgeting money. it's budgeting salt and glucose and water and oxygen and all the things that your cells need to keep you alive and well. And you can think about spending resources like spending glucose, spending oxygen, spending water, and so on, the way that you would spend money. And you can think about, making deposits into your body budget. So, what are the most expensive things that your brain can do? Well, it can move your body, physically move your body. Like getting up in the morning is a metabolically expensive thing to do. And when your brain is predicting that you need that metabolic boost, it directs your adrenal glands to secrete cortisol. So people think about cortisol as a stress hormone, but cortisol is actually just a hormone that gets glucose into your bloodstream fast because your brain believes you need to do something that's requires a lot of energy, like getting out of bed in the morning or exercising. The other thing that is a big expenditure is learning something new. So when things are predictable to you and you can predict what's happening pretty easily, that's a sort of that's a less expensive mode for your brain to be in. But when something is novel or uncertain, or you can't predict what's going to happen next, that's actually much more expensive, metabolically speaking. And we can think about deposits into our body budgets as when we sleep, when we drink water, when we eat healthfully. Even, a hug from a friend, a close friend, can be sort of figuratively speaking like a deposit. And we can think about things like exercise as, spending to make an investment in the future, an investment that you expect to get a return on. And so the idea here is that really brains, the most important job your brain has is not really thinking or feeling or seeing. It's actually running this budget for your body. And you think and see and feel in the service of running that budget. And it doesn't feel that way to us. That's not how we experience our lives. Our brains are masters of deception, right? They seamlessly control our actions and create our experiences and lead us to believe that the experiences actually reveal how the brain works, but our experiences don't reveal how the brain works.
It's interesting too how in the beginning you talk about success in terms of if we get a basic idea of what's ahead and figure out whether it's good or bad, we know whether, okay, let's go up there because it looks like food, or let's not go up there because it looks like it might eat us. And that ties into some other scientists I've interviewed, which is like our perception of reality is not reality at all. It's just a way for us to stay alive and reproduce.
Yeah, so that's lesson 4.
Sorry, I jumped.
But sure, and actually in how emotions are made, I go into that in much more detail. But yeah, I mean, to us, the way we experience the world is like our eyes are a window onto what's happening in the world, and that we see things the way a camera sees things. That we're just capturing really what's out there, but that's actually not what's happening at all under the hood. And that's what makes it so really cool when you learn what is happening, because it's so different from your everyday experience of your own life.
It's so funny because, and this is another lesson that I'm going to get out of order, but when you tell me that's lesson 4, there's part of me that goes, oh, I failed.
No.
So now I have to be more careful. I get all
No. We no. This is all about being curious. It's all about being curious. It's not about being evaluated at all.
Well, so hopefully the first lesson is this idea of triune, the brain divided into 3 parts that we've all learned and still learn according to you, and $180 textbooks that my poor daughter has to carry around when it's out of date as soon as it's written. I'm getting myself started. Never mind.
That we can have another conversation. We can have a whole other conversation about that. Yeah, for sure.
Richard Feynman talking about that. But yeah, so you're saying, and then I'm going, oh my gosh, he's saying something bad about Carl Sagan. and the dragons of Eden. And I'm thinking, but it's Carl Sagan. How can she? But
Yeah.
he's wrong, according to you.
Well, it's not just according to me. I
Yeah,
mean, actually,
right.
this is not this particular topic is not something that I discovered. I mean, it's not my research that toppled the triune brain. So this idea that the brain evolved in sedimentary layers with, an inner lizard, like a lizard brain for instincts, and a limbic system, limbic meaning border. So the areas of the brain that border this inner lizard called the limbic system, which is supposedly for motion, and later on top of that, is your cerebral cortex, which is supposed to be for thinking. Carl Sagan didn't come up with that idea. That idea really has been around at least for a century and was really solidified by a neuroscientist named Paul MacLean in the 1940s and 50s. And right when he was initially publishing these ideas, they were immediately criticized by neuroscientists, other neuroscientists, and some of whom were extremely well known. And in the 1960s and 70s, neuroscientists who were able to, peer deep into the molecular structure of cells and look at the genes that cells, neurons, and other brain cells contained, could see that that's not at all how the brain evolved. Carl Sagan, what I'll say, I'll just say two things about this. One is that in 1977, when Carl Sagan published The Dragons of Eden, which won a Pulitzer Prize, he was probably a brilliant cosmologist, but he wasn't a neuroscientist. And it's a good lesson for neuroscientists, actually for scientists in general, I should say, to be humble about what they write about. When I'm writing about neuroscience, I can write much more boldly than when I'm writing about molecular genetics. I'm not, and so there's no way that you can avoid potentially making a mistake when you're writing about something that is not your own area of expertise. And so you have to be super careful when you do that. That would be the first thing I would say. The second thing that I would say is that one of the really nice things about science is that it's not supposed to be functioning on the basis of authority. It doesn't matter who someone is. Darwin was wrong about some things too, as was Einstein and even Newton. So the great scientists of Western civilization did wonderful, amazing things, but they also were sometimes wrong. And that's the lovely thing about science. Science is all about having a hypothesis, an idea, and testing it against observations. And it doesn't matter who you are, you can be wrong. The data can tell you that you're wrong. So yes, Carl Sagan may have been right about many things, and he was a fantastic science communicator, and he may have even been like a super nice guy, but he definitely was wrong about this. And we've known for at least 50 years that brains didn't evolve that way. So this myth should not be in textbooks. It should not be in expensive executive training programs. And it's certainly, we should start looking at things like the law and economics and other institutions in our culture, which are founded on this myth, really. It's a morality story that comes from Plato that got tattooed onto the anatomy of the brain, and it just isn't that's not how the brain is structured, and it's not how the brain evolved.
And what's so funny is I was so comfortable before reading this book with the idea of the reptilian brain and the neocortex, and that's what makes us different than monkeys. And I'm going to other lessons now. And what's so funny is that I'm so comfortable with it, which is also part of your lesson. I feel like you're taking me out of my comfort zone because I had this idea of the limbic system, the id, the ego, and the superego. And now I'm at sea, or I was, and now I understand it much better. Oh, and that's the other thing I said in the introduction is that since it's so accessible, it's a lot easier to digest. And if if you're brave enough, you can go into the actual additional deeper stuff that you do. But yeah, it's so accessible. You can actually, and this, again, I'm talking about the very thing, is your mind is malleable enough to take all this in and say, yeah, that seems reasonable to me.
Well, I want to thank you so much for those comments, because I worked really hard to make this book a little bit like a choose your own adventure. You can just read the essays. Yeah, just read the essays. And the essays are really written for people who don't necessarily think of themselves as people who read popular science. So they're written as an invitation, in a sense, to people who maybe aren't that interested in science or don't have much of a science background. And you can take away a couple of nuggets of neuroscience from each essay. Talk to your friends and family, entertain them with a couple of, interesting tidbits that you learned. And then maybe think about them in the larger set of questions about what it means to be human, and what kind of a human are you, and who do you want to be. But if you are someone who's interested in the details of science, then there's an appendix. And then, as you said, there are web notes. And in the web notes contain references for every point that I make in the essays. And the references are linked in the web notes to specific sentences in the essay, so that people can go and actually go read the scientific evidence that is behind the points that I'm making in the essays. But the essays themselves stand on their own, and they can exist without any reference to specific published papers.
Yeah, it's nice that everything you say there, you back up every sentence, like you said. It's also the other reason it's so accessible is the metaphors, analogies. Kind of like the analogy of our own perception of reality. But one I really liked, in addition to the budget one being first, is the kitchen.
Mm-hmm.
Talk about that a little bit.
Sure. So sometimes, people will write, sometimes even scientists will write that, humans have a huge cerebral cortex. And so this must mean that, we're very, very rational creatures. I think anybody who has lived in any part of the Western world for the last 4 years would maybe question just how rational we are as a species. But in any case, that's the argument. And but the thing is that you can't really think about the size of a part of your brain without thinking about the size of your whole brain. And so it turns out that well, let me say the analogy, and then I'll lead it back to the brain. So, if you were thinking about let's say you walked into somebody's house and they had a huge kitchen, you might immediately think to yourself, wow, this is definitely a place I want to have dinner, because these people must be awesome cooks, because look at the size of their kitchen. But you can't really know whether the kitchen has a special function until you look at it in relation to the rest of the size of the house. So if it's a big kitchen in a huge house, huge kitchen in a huge house means the kitchen is just the average size scaled up for that size house. But if there's a huge kitchen in a small house, that implies that the kitchen has a special function. Maybe these people are chefs, and maybe that is a place where you want to definitely eat dinner. So when we look at the size of the human cerebral cortex, it's about the size that you would expect it to be, given that we are primates of a certain whose brain size is what it is. So, we are primates. As primates, actually, as mammals, we have pretty big brains, and so our cerebral cortex is about as big as you would expect for someone who has a brain of our size. Elephants have much larger cerebral cortex than we do, because they have much larger brains than we do. And if you took an elephant and you shrunk it down to the size, an elephant's brain shrunk it down to the size of a human brain, it would have approximately the size cortex that we have. And if you took, a macaque brain and you blew it up to the size of a human brain, then, the macaque would have a cerebral cortex was about the same, which is about the same size, as our cerebral cortex. Now, so size, we do have a large cerebral cortex, but that's because we have large brains. And there are some micro wiring differences in the human brain that make it I don't want to say special, because like every brain is special in a sense. Every species has its own advantages, but there are some wiring differences that humans evolved that make our brains slightly different from, say, chimpanzee brain or macaque brain. And I talk about those a little bit in lesson 7. And I'm happy to say more about those now. But basically, our cerebral cortex isn't special because of its size. It's about the size that you would expect given the size of the whole brain that we have. And therefore, it doesn't really need a special explanation for its size.
And again, it runs totally counter to my intuitive education. But to continue, and to continue in the culinary aspect of this, you talk about the meatloaf brain, pocket knife brain, which are terms that I don't think anybody has ever said in the history of the human race, unless somebody else said it. But I would never expect those words to be together.
No, but what I did do was I borrowed from some other writing on the mind. And so Steve Pinker, for example, just has written about the mind, and he takes a view that is somewhat different from my view. But his, when he was explaining his view, he caricatured, a meatloaf mind, a mind that is, where every cell in the mind is this, or every not, he wasn't really talking about the brain, so he wasn't talking about cells, but like every aspect of the mind is the same. It's kind of a blank slate, and then the mind learns, and everything that the mind can do, it can do only because of learning, as if there's nothing genetic really going on. And he called that the meatloaf mind. And so I borrowed that and turned it into a meatloaf brain. And similarly, the evolutionary anthropologist, John Tooby, and Leah Codismides, his evolutionary psychologist partner, had talked about the pocket knife mind, as if, we have these modules in our minds that are very specific for specific functions. And so I took that and conjured it into the pocket knife brain. And in the appendix is of the book actually not only gives more details about the essays, but it also gives credit to other scholars when I borrow a turn of phrase, or maybe bastardize a turn of phrase, from another scholar. I give them credit, not for the bastardization, but I give them credit for their original insight. So, so you can see that. You can find the references to their work in the appendix, actually.
And it's funny, another thing that reminded me that I'm using the tool is that in my mind, I see this very complex Swiss Army knife, and then I see the toothpick and the tweezers and the scissors, and in my mind, I'm equating them to certain things that we do that are tweezer-like things, and certain things we do that are toothpick-like things, and certain things we do that are scissors and knives and screwdrivers that actually correspond in some funny way to things we actually do in
yeah. And I think that was the original reason for using that analogy. But what I would say is that, for at least 150 years, scientists have been pondering over whether there are specific parts of the brain that are dedicated for specific psychological functions. And that is a debate that continues to rage, but the weight of the evidence suggests no. That in fact, it's not that any given neuron can do anything, but it can do more than one thing when it comes to something psychological. And so even something like, for example, the neurons in the back part of the brain called the occipital lobe, these are referred to as visual neurons, visual cortex, because these are neurons that represent information that comes from your retina. However, they also carry the information about hearing and about touch. We still call them visual neurons, but they actually perform other functions. And that's pretty much true of every set of neurons in your brain that have ever been studied, or in any brain, actually. And so again, it's not that any given neuron can do anything, it's just it can do more than one thing. And there's a really wonderful book that was written by a philosopher called After Phrenology, I think it's called, or Beyond Phrenology. I think it's After Phrenology. Phrenology being a reference to the 19th century science of assuming that different bumps on your skull correspond to different parts of the mind that do different functions, kind of like, Lego blocks or like a Swiss Army knife. And it's just the weight of evidence at this point just suggests that that is not how brains are organized, and it is not how brains function.
So it's always been funny to me. I always thought the occipital lobe, why is it back there? Shouldn't it be up here? It's like a long way to go to get the information from here back to here, but that's all wrong too. One of the things you talk about in that lesson, the second lesson, is complexity. And it's like when I get on an airplane and it goes up in the air, there's still part of me that goes, how the hell is this happening? How can we do this? So I was wondering, in your own mind, if the complexity of it is still awe-inspiring to you.
Absolutely. I would say, if you think about it right now, something is happening. Many things are happening, but something's happening right now in 128 billion cells that are participating they're talking to each other in a constant conversation with each other and with your brain, and with your body and with what's going on around you in the world. And because of that, you are having thoughts that you can implant in my head, and then something's happening in 128 billion neurons in my brain. If that's not awe-inspiring, if that doesn't inspire wonder and awe, I don't know what does, actually. Yes, I think that when you sit down and think about it, like right now, for example, we're sitting here, we're talking to each other. Maybe you have listeners who are listening, and you're not really aware of the fact that there is a whole drama going on inside your body of tremendous complexity that you are completely unaware of. And that drama is having a constant conversation with those 128 billion neurons. That's just like, that's like a part of the visual spectrum that you can't see, like radio waves. Or it's just, it's fascinating, in part because it's really flying under the radar. It's not something that we can sense, but it's definitely there, and it's affecting every moment of your life.
I think it was last year, because I can't remember the books, but I dealt with one author who had written about consciousness and did it very clinically and anatomically, and the other one who basically was saying consciousness is just this illusion that allows us to exist because we perceive reality in a necessary way for us to continue things going on. And then I said to them, what if it's a solipsistic universe? And it kind of burst their balloon, and they both got mad at me. And then, of course, but if it was solipsistic, either I'm not talking to you or you're not talking to me. But it kind of interrupted their science, and they seemed very upset about it. But if it is solipsistic, it really doesn't matter.
Yeah. So what I would say, though, is that, it's in a sense, it's a philosophical question, but in a sense, it's also a neuroscience question, because, infant brains are not miniature adult brains. They're brains that are waiting for wiring instructions from the world. That's how we evolved. We have the kind of nature that requires nurture. Our brains wire themselves to the world that we live in. And so what's happening is that because brains are born incomplete, they're born under construction, they're wiring themselves to take in and represent the statistical regularities of sights and sounds and smells and, things going on inside the body. And so the really cool thing is that when the way that we experience the world is that we see things, we might hear things, we react to those things, um, and but that's actually not what's happening under the hood. What's happening under the hood is that using past experiences, your brain is these past experiences that you've learned from, taking in information, and that's affected the wiring of your brain. These past experiences are automatically generating predictions. So if I ask you, if let's say you were predicting that you would see an apple, and you pick up a red thing and it's an apple, and in your mind's eye, your brain actually would be predicting the color of the apple. Well, let's say there's no apple there yet, but I just say to you, imagine in your mind's eye that you see an apple. What do you see in your mind's eye?
An apple.
Yeah, but what do you see? What color is it?
A certain color red, or perhaps yellow, or perhaps
right. So but so say a red round apple. Most people can do this, and then you can imagine grasping the apple, you can imagine biting into the apple, hearing the crunch of the apple, the tart taste of the apple. It's not the same as having a real apple there, but it's you can vividly see an apple, and to some extent hear it and taste it and so on.
It's like when you were talking about chocolate, and you were actually
exactly.
Yeah.
And this is what your brain is doing when it's making a prediction. It's actually starting to generate the neural changes, the neural firing, to prepare to see the apple, taste the apple, smell the apple, chew the apple, and so on. So then what if I actually pull out an actual apple and I hand it to you? If that apple is exactly the way that you predicted it, the sense data from that apple confirms the neural firing in your brain, and there's no new information there. So that's it. Your perception of that apple is only deriving from what's inside your own head.
Right. It's like when you had that birthday party for your daughter and you gave them excellent foods, but in these horrible, like the urine sample.
Right.
It's like that. You don't get what you expect. But it's interesting about babies, because there's some people say that a baby just born is a Buddha baby. It hasn't had the chance to experience samsara, this thing that we're in, this suffering, and that, but it's not like your creature. It's not like the ambioxis. It's something different. You have this human being with a brain, perhaps with a mind, but it's born in such a fashion that it has none of the things that you're saying. It doesn't have the ability to envision anything because it hasn't yet done that. The way you talk about the mother's face is just far enough away that the baby can focus on it and learn how to see things, or edges with a box.
Right. I mean, basically, babies' brains are born under construction. If light does not strike the retina of a baby's brain continuously, the baby's brain won't, the visual system won't finish wiring itself, and the baby won't be able to see normally. The same thing is true really for every sense we have. But babies are born with the capacity to take in sense data from the world and learn the statistical regularities of the sensory patterns, and that's what finishes wiring their brains, and that's what basically creates the substrate for a neurotypical functioning brain in the future. The wiring instructions come from the world, and part of that world is social. Part of that world is curated and constructed by the humans who take care of that baby. So this is, to some extent, this is lesson 3, but there are also tidbits of this idea, and the science behind it in other lessons as well. And it's a really fascinating thing. I will tell you that, when I first started learning about brain development, I started looking at very, very, very young infants in a very, very, very different way. They just look like they're little blobs, kind of sitting there, but that's like, there's a lot going on under that hood, man. They're really interesting little creatures.
Well, one of the things that really hit home for me was that two of my daughters we adopted from China, and they were both in orphanages. One was in an orphanage that was like Disney World, Annie's, and she just was thriving and running around and had toys and was playing with 10 other kids and wonderful teachers, caregivers. And Samantha was put in an orphanage. It wasn't their fault. They just didn't have the capacity. It's like with COVID. They didn't have.
Mm-hmm.
So she was in a 4x4 sheet of plywood with a hole in the middle of it. They put her in it and they took her out only to go to the bathroom. And she's amazing. She's overcome all these challenges, but it really struck home because the difference at that time was just absolutely striking. And it's almost as if you were writing about them.
Well, thank you for sharing that. It pains me to hear it, and particularly because I understand what it can possibly mean for a developing brain. There's so much to say about that, and unfortunately, we don't have the time to say it. But
I just had to bring it up because
yeah. Well, thank you for sharing that.
Sure.
Yeah.
And then okay, so let's move on then to.
Well, I think we only were supposed to be until 2
Oh,
o'clock,
okay. I
right?
didn't know
Yeah.
Well, okay, we're good. I think the readers, and this will be, as I have an independent bookstore, this will be on the front desk, and it has a great cover. So people say you can't judge a book by its cover, but everyone who comes into my bookstore does.
Yeah.
So anyway, yeah, thanks very much for taking the time to be here. And yes, as I said, it's an excellent book. And the most important thing about it is, yes, with regard to popular science, some people just walk by. I don't think they'll walk by this book.
Well, thank you for saying that. Thank you for saying that. And thank you so much for your interest and for the great conversation. I really appreciate it.
Yeah. Thanks very much. Bye-bye.
Okay, take care. Bye.